All right, so for the previous problem, I didn't pay attention to how many decimals we are asked to round. So I think this was just to 3 decimals, so you would drop the 8. So just pay attention when you do the actual homework that you round to how many decimals they asked for. All right, so let's get down to the last problem. So the last problem is given the formula for the concentration of a drug in a patient's bloodstream after T hours. So you're giving the drug, and then after 2 hours, you're measuring the concentration. After 3 hours, you're measuring the concentration. And this is the formula. And C is measured in milligrams per liter. What is the initial concentration of the drug? Well, we can just read that from the formula, because we know that this value right here, 9, is the initial concentration. So the initial concentration is 9. So this is the answer. You're just reading it off the formula. As you can see, the factor right here is 0.74, so this is a decrease, right? The concentration actually decreases, C of T. So this is going to be an exponential decay, and it starts at 9. My pen is going out. So it starts at 9 and it decreases. This is T measured in hours, and this is the concentration measured in milligrams per liter. So I'm interested to solve for the time. I'm interested to find the time T when the concentration decreases to 70% of its initial level. So what does that mean? I'm interested to see the time. So C of T, let me copy down the formula, is 9 times 0.74 to the T. So I'm interested to find the time T when the concentration, so when the result is 70% of the initial level, and the initial level is 9. So I'm interested to find when the output, this, is equal to 70% of 9. I don't know what just happened in here. But 70% of 9 just means 0.7 times 9. And then the formula is 9 equals 0.74 T. So I want to basically find graphically when these two functions, this exponential decay function, and when this, again, this is just a value, it's just a constant. So 0.7 times 9, 0.7 times 9 is 6.3. So I'm interested to see when the concentration is down to 6.3. So how we're going to do this graphically? Again, we are going to go into y, and we're going to graph the exponential decay function. So 9 times 0.74 to the power, I'm just going to use x. It doesn't matter what I call the input, x, t, x. And then I want to see when it's equal to 6.3. How long? For what x? How long does it take to concentration to reach 6.3? So let's see. We need to change the window. So remember, x is measured in hours, starts at 0, and it goes for some hours, and I'm interested to see where, for what, after how many hours the concentration is down to 6.3. So for x, I kind of need to guess. So let's look at 10 hours. So for x goes from 0 hours to 10 hours, and the y, well, it starts at 9, so I have to go at least up to 9. So let's go up to 10. Let's graph it. So this, it starts at 9, the concentration decreases over time. And then, ooh, it looks like it reaches 6.3 pretty fast. So this horizontal line represents 6.3, and I want to find the intersection so that I get for what x, for what t or x is the concentration 6.3. So second, trace, find the intersection. The first curve is that one, enter, enter, and then a third enter. There you go. The intersection happens after happens for 1.18. So after 1.18 hours, the concentration is 6.3 milligrams per liter. So you would say that the answer for B is 1.18 hours. 2 decimal places, so that's good. Okay, so just keep in mind what we actually did. We solved for x when x is an exponent, and we're going to learn how to do this algebraically rather than do it graphically.